The position of an object at any time t is given by a function s of t. Determine the velocity of the object at any time t. Determine the acceleration of the object at any time t. Does the object stop at a point? If so, where? So this is the question which we are going to solve today. We are given the position of an object by means of a function which is with respect to t. Okay, we are going to identify the velocity. Of course, we are going to use the concept of differential calculus to identify the velocity and acceleration. Okay, the derivative of a function, as we all know, it is nothing but the change, difference. So we know that very well. So a velocity of an object, in the sense, if an object is going to move from one place to other, the change in position, okay, the difference between the first and the second position, so we can understand it in any way possible. So this becomes the velocity of an object. So to identify the velocity by means of differential calculus, we are going to identify the first derivative of the given function. So that will give us the change in the position of the object, which is nothing but the velocity of the object. That is the speed with which the object is moving from one position to the other position, which becomes the velocity. Next, acceleration, in the sense, acceleration is nothing but the change with respect to velocity and also the direction of an object. So I repeat, it is nothing but the rate with which the velocity changes with time in both speed and direction. So in order to identify the acceleration of the object, that is the change in velocity with respect to direction also. So change in velocity, in the sense, it is absolutely understood that we are going to identify the derivative of the velocity. So to be very clear, we are going to identify the second derivative of the given function. So these are general concepts we need to know. Velocity of an object can be identified by taking the first derivative of the function. Acceleration of an object can be identified by taking the second derivative of the function. Since acceleration is nothing but the change in velocity with respect to time. That's why. Okay. The third subdivision, does the object stop at a point? If so, where? So this third question we'll discuss at the last. Okay. Now first let's find out the velocity of the object and the acceleration of the object. Let's start. Given the function s of t, this is nothing but the question. We are going to identify the velocity. So to find the velocity, we are going to identify s dash of t. That is the first derivative of the given function. The function is with respect to t, so we are going to identify the derivative also with respect to t only. So this is derived in the pattern, that is when we are going to differentiate x power n, in the sense what we do, it is differentiated as nx power n minus 1. So that pattern only we are going to follow throughout. So the coefficient 3, let's have it as this. T power 4 we can differentiate it as 4t power 4 minus 1, which is 4t cube, minus 40, let's have it as it is. T cube we are going to identify the differentiate as 3t power 3 minus 1, that is 2. Next, 126, let's have it as it is. T square, let's identify with the derivative as 2t, minus 9, it's a constant, derivative of a constant term is 0. Okay, so now we have got with the derivative, let's simplify this. So 3 into 4, which is 12t cube, minus 40 into 3t square, that is again 120t square, 126 into 2. 2 into 6, 12, 1 carry over, 2 into 2, 4 and 5, 2 into 1, 2. So 252t minus 0, let's omit it. Okay, now this is nothing but the velocity of the object. Okay, so this is s dash of t. Let's try to simplify this further. We have t as a common factor throughout. Let's take t outside. So this becomes 12t square minus 120t plus 252, that's it. Okay, now 12, it is a common term or common factor for the entire function within the bracket. So let's remove 12 outside. So this is 12t into t square minus 10t, 252, which is nothing but 21. That is 12 into 21, which is 252. That's why we have taken 12 outside. Okay. So now let's try to factorize this quadratic equation for convenience. Why we are doing all this? The sum is complete here, but we are proceeding further. That I'll say you at the last. Okay. So this is t square minus 10t plus 21. It is a quadratic expression which we are going to factorize. So we are going to use the t method. Let's have 21 at the top minus 10 in the bottom. Now we are supposed to use two integers whose product is going to be 21 and sum is going to be minus 10. So that's going to be 7 into 3. Minus 7 into minus 3 is plus 21. Minus 7 minus 3 is minus 10. That's it. So this is 12t into t minus 7 into t minus 3. So this is nothing but s dash of t, which is nothing but the velocity of the object. Next we are going to identify the acceleration. So now to find the acceleration, we are actually going to identify the second derivative of the given function, or else we are going to identify the derivative of the velocity. So it's easy to take the derivative of the velocity. So let's do the same. Let's take this one. It's easy for us to identify with the derivative. So we are going to identify the derivative of the velocity here. See to that we are very careful. So that becomes s double dash of t, or else the other way is take the function, identify the derivative, once again identify the derivative, that becomes the acceleration. So s double dash of t, which means the second derivative of the given function. So let's find out. This is coefficient 12, have it as it is. T cube can be identified with the derivative as 3t square minus 120 as it is. T squared can be identified with the derivative as 2t. 252t can be written as 252 into 1. That's nothing but 252. So now this is 12 into 3, 36t square minus 120 into 2, 240t plus 252. That's it. So this is going to be s double dash of t, which is nothing but the acceleration of the object. That is the change in the velocity with respect to the time and direction. Last subdivision, we are going to check whether the object stops at a point. Okay, just imagine when an object will have a stop at a point. Of course, when it is not moving, right? So when the object is not moving, it is definitely understood that the object is going to stop at a point. Same way, here also we have identified the velocity of the object, that is the movement of the object from one position to the other, the speed at which the object is moving from one position to other. So if suppose the speed is not there, okay, suppose if the speed is 0 at a point, it means the object is not moving, right? So that thing only we are going to do it here. The velocity of the object we know. We are going to find out when all the velocity becomes 0. Okay, so wherever the velocity becomes 0, there all the object is going to be in the still position. That is, it's not going to move. Okay, so since velocity of the object is equal to, let's take the final statement, 12t into t minus 7 into t minus 3. Okay, so the object will stop at a point when the velocity is equal to 0. So therefore 12t into t minus 7 into t minus 3 equal to 0 implies, okay, the object stops at a point. Okay, so let's equate each of the term to 0. That is why I told you to find out the final statement which is factorized completely, or else we would have stopped here. But we had taken the common factors outside and we have factorized the equation for this purpose only. Now it is easy for us to identify where all the object is stopping at a point, that is where all the velocity becomes 0. So when t is equal to 0, see, right, we are equating t to 0, and t is equal to 7, t is equal to 3. This velocity becomes 0. Can you understand? If you substitute t equal to 0, this statement is 0 again. When t is equal to 7, this statement is 0. When you substitute t is equal to 0, this statement is 0. Okay. So what happens now at all these points when t is equal to 0, 7 and 3? In these positions all, the object is not having a velocity, which means the object is in the still position. That is, it is not moving. It's not in motion. That's it. Okay. Thank you.